going to look at composite volumes, which is high merit at years 10 and 11. Before we go into volume, we're going to quickly revise how we do things with complex composite areas. If we have a difficult shape, this pentagon, then we divide it into two simpler shapes, the rectangle and triangle, that compose it, and we add their area. We can also do it by subtraction. So if we have a rectangle with the corner cut off, then far and away the easiest way to calculate the area is to take the rectangle and cut the corner off. So we have the rectangle's area less the triangle's area. Well, we can apply those techniques to volume. The volume on the left is made up of the cuboid and the triangular prism on the right, and their volumes together equal the original volume. And we can also do it by subtraction. This is a pipe, a hollow cylinder, so it is the outside volume take away the missing inside volume. In this case, we don't have to do it that way. We could do it the standard way for doing volume, which is find the end cross-sectional area, the outer circle, take away the inner circle, that would give us an area, and then we would multiply by the height of the pipe. But sometimes, for the harder questions, subtraction is the only method. For example, if we were to try and estimate the amount of stone in this hemisphere basin, then our only method is to take a half sphere of the outside and then subtract the missing half sphere from the inside. The most common time that we need to do this is when we have truncated shapes, and here is a truncated cone, a cone with the top taken off. Well, in order to calculate its volume, we would calculate the original volume of the cone and then subtract the missing portion. The difficulty comes in calculating the heights of the original cone and the missing cone. So, for example, if we have this truncated cone, base diameter is 12, top diameter is 4, and it's 6 high, well, we have to calculate what it was before the top was taken off. So we extend it up and we apply some ratio thinking. It must have been originally 9 centimeters high, and I do that by thinking it originally started at 12 centimeters. By the time it's got to 4 centimeters wide, it is 2/3 of the way to 0, because 4 is 1/3 of 12. So it has made it 2/3 by the time it gets to 4. So there's 1/3 remaining. So there was an extra 3 centimeters on the top of it. And we then take the volume of a cone, 1/3 pi the bottom radius squared times the height. And our truncated cone's volume is those numbers for the large original cone minus the bit that's missing. So in this case, it's these numbers here. The radius is 6, the height was 9, the radius at the top is 2, and the height is 3. Note that the height is 9 because we are going from the base to the original peak. Stick it in the calculator and we get 326.7 centimeters cubed. Now we can estimate that volume as a check for how well we did, or just as a quick measure, and we would estimate it by taking the cylinder with the average radius and the same height. Well, the original radius was 12 and it went down to 4, so the average diameter is 8, so the average radius is 4, and that cylinder would be 6 high. We stick that in for the volume of a cylinder, and we find that we're out by about 10%, but it does give us a rule of thumb, and it's a good check that you've done the volume the truncated way correctly. Let's do it again. Take a truncated square-based pyramid. It started with sides 8 meters long and ends 6 meters, and it's 1 point high vertically. So we extend it up, and we have to work out how high it was before it was truncated. Well, 8 to 6 is a quarter of the way to 0. We've lost 2, so we've got 3 quarters to go. If 1 quarter is 1.5, then 3 quarters is 4.5. It was originally 6 meters high. The volume of a pyramid is 1/3 to 2 base edges times the height. The truncated one is the big base times height minus the small one. We stick in our values and we get 74 meters cubed. If I want to estimate that one, the matching cuboid would have an average side length of 7 and a height of 1.5, and it comes out surprisingly close. Generally, if these two numbers are similar, then the estimated way will give a very close measure, whereas in the case of the truncated cone, it had already tapered too much to be accurate. So what do? When we have complicated shapes, we can do it by subtraction. The volume, if there's a piece missing, is the volume without the piece missing minus the volume of the missing piece. And for truncated ones, we calculate what the original cone was and then take away the piece that's missing on the top.